If you open a digitized copy of a book titled Advanced Arithmetic, you expect to see numbers, formulas, and dense equations. But if you actually flick through the opening of this specific file, you get something entirely different. The first 26 digitized frames contain exactly one image with ink. The other 25 are completely blank. To a mathematician or a casual reader, this looks like a mistake. It seems like a scanning glitch, an operator falling asleep at the wheel, or a massive waste of server storage. To a digital archivist, these frames represent a deliberate dataset, captured with the same rigor as the text itself. Mass digitization operations follow strict international standards, like the FADGI guidelines, which govern exactly how cultural heritage materials must be captured. Under these protocols, high-fidelity archival digitization does not simply extract two-dimensional text. It creates a precise one-to-one structural surrogate of a three-dimensional physical object. When most of us think about scanning a book, we think about optical character recognition, or OCR. That is the utilitarian process of turning a picture of a page into searchable, highlightable text. But OCR only cares about the words. It strips away the physical context, the binding and the history of the object itself in favor of pure information. Books like this copy of Advanced Arithmetic exist as physical artifacts. They survived decades of circulation in places like the University of Michigan library system before ever seeing a digital censor. To preserve an artifact properly, archivists have to map its complete structural boundaries. That includes every protective layer of paper and cardboard that encases the actual text block. So to understand what we're looking at in this digital file, we need to temporarily ignore the mathematics and look strictly at the book's housing. In archival science, an absence of text does not mean an absence of data. Empty space is verifiable structure of evidence. Let's look at the only non-blank frame in that opening sequence, the bookplate. It displays the University of Michigan's heraldic shield and motto. Below the crest is an empty rectangular field, where librarians manually stamped unique acquisition numbers when the physical book arrived. This glued-in tracking method was the precursor to the massive physical card catalog systems required to index thousands of circulating volumes. Today, the information on this physical plate translates directly into modern digital metadata fields, like a MARC record. It proves this specific physical copy's journey through a distinct institution. By capturing this plate first, the file establishes a strict chain of custody. It locks the artifact's provenance into the database before presenting a single page of core text. That leaves us with the 25 identical blank pages that follow it. Historical bindings are constructed using quires, or signatures. Binders group together thick, unprinted pages at the beginning and end of a volume to reinforce the heavy text block. The first digital blank frame corresponds exactly to the paste down, the paper glued directly inside the front cover. The following frames map to the end papers and flyleaves, which act as a physical buffer protecting the title page from the stiff binding. Capturing these blanks in high resolution records the specific wear, the tear, and even the exact paper stock thickness chosen by the original binder. Those 25 empty frames represent an exact layer-by-layer architectural blueprint of the physical book's protective casing. In the past, archival work relied on manual, selective techniques. Photographers using microfilm might omit pages with no text to save film. Modern mass digitization relies on strict automation, utilizing hardware like the non-destructive V-shaped book scanner. A V-cradle and a precisely angled glass platen work in tandem, safely flattening fragile paper to photograph it without breaking the aging spine. A dual camera array captures the left page, the verso, and right page, the recto, simultaneously with every physical leaf turn. Skipping a blank page breaks this mechanical sequence, causing a cataclysmic error where every subsequent page displays on the wrong side of the screen. The hardware is completely blind to ink density. It only registers physical page turns. Deleting an empty capture corrupts the entire structural dataset. This standardizes the output into a sequence of identical white rectangles. It looks monotonous, almost pointless to the human eye. But quality assurance algorithms rely on this unbroken rhythm. They use the sequence to verify that the physical leaf count of the actual book matches the digital frame count perfectly. If a physical page had been torn out of this 100-year-old volume decades ago, a disruption in the expected sequence of blanks would immediately flag the physical damage for the archivist. A human operator might instinctively want to curate the scan, to delete the blank space and skip ahead to the text. But strict preservation protocols forbid any interference. The exhaustive presence of these blanks provides a mathematical guarantee. When the text finally begins, the user knows with absolute certainty that no data has been omitted. We started by looking at a frustrating lack of mathematical equations, but decoding those empty frames revealed a detailed map of institutional history and physical architecture. Those two-dimensional digital frames synthesize perfectly to represent a three-dimensional object. Accessing a high-tier digital archive provides scholars with the complete structural architecture of the original artifact. They are interacting with a digital surrogate. It allows a user thousands of miles away to navigate a flattened, high-fidelity mapping of a very specific physical space. In the rigorous science of digital preservation, a blank page is never an absence of information. It is the ultimate proof of an uncompromised historical reality.